In this video, we're going to look at the Big Bang. And if you're following along in OpenStax, that's chapter 29. So in order to get the idea of the Big Bang, we first have to talk about the fact that the universe is expanding. And the person who's responsible for discovering this is the astronomer Edwin Hubble. And you would know Edwin Hubble if you've heard of the Hubble Space Telescope. It's named for him. He didn't put up the telescope, but it's named in his honor. And what Hubble discovered was something involving the Doppler shift. Now, you know about the Doppler shift if you've heard an ambulance or a police siren or a fire truck go by. It's very high pitched as it comes towards you, and then as it goes away, the pitch changes. The sound of a siren changes. And what he was finding was, looking at distant galaxies, as the galaxies were receding, or if the galaxies were moving away, the wavelengths were lengthening. And that's called a redshift. It turns out, if you look at the light down here, if we look at red light, it has what's called a very long wavelength. And a wavelength is nothing fancy. It's just the distance between two waves. You have to pick the same point. But it's not a fancy measurement. It's just the distance between the two wavelengths. Now, if the galaxy was moving closer to us, we would see what's called a blue shift. In other words, the light would lean more towards the blue. The wavelengths would be getting closer together. And what he found was only very nearby galaxies would blue shift, galaxies in what are called a local cluster, or just ones that are pretty close to us. All of the distant galaxies were receding, had this red shift. So this is the experimental evidence that the universe is expanding. Now, a good question would be, well, what is it expanding into? If we blow up a balloon, well, we'd say, well, the balloon is expanding into the room. The answer to that is, well, nothing. It's kind of an odd thing. It's not that the universe is expanding into something, the way the balloon would expand into a room. It's that space itself is increasing. And it's like dots on a balloon. Let's show you that on this slide here. So if we think about each of these dots as galaxies, and let's have some light here. We'll draw a little light wavelength. I like this picture here between the galaxies. So that would be light coming from the stars in one galaxy, maybe coming to Earth where we can see it. If we add a little more air to the balloon, which is what we see on the right, we see that the distance between the galaxies has definitely increased. I'll just pick these two as an example. And what we would see is, because we stretch the surface of the balloon, we have a red shift, where the light's wavelength becomes longer. And it's space itself that expanded. Now, a real interesting question would be, well, if these distant galaxies are getting further and further away and space is expanding, is the distance between our planets increasing? In other words, is Mars getting further away from us every year, or is Jupiter getting further and further away? And the answer is no. Within our solar system, the gravity is strong enough to control things, and that space is not changing. The space between our atoms isn't changing. And even, in fact, gravity is strong enough to keep local galaxy clusters in control. So nearby galaxies, that space isn't increasing. It's the distant galaxies and the space between galaxies that are pretty far apart. Now, let's talk about the rate of expansion. When we learned about the sun, we learned about this tension between gravity and the pressure in the sun wanting to expand it. And it turns out we could say, well, is the gravity of all the planets and the stars enough to hold everything together? But it turns out gravity is not halting expansion. Supernova, specifically type 1 supernova, but we'll just say supernova for right now, are used as what are called standard candles. In other words, to measure how far apart these distant galaxies are, we have to have a way to think about that, or a way to measure it. And it turns out that all these supernovae are roughly the same brightness. So if we know how bright the supernova is, we know how far away it is. And the expansion turns out is accelerating. So let's look at these pictures down here before we talk about that. Let's look at these pictures. So you can see a supernova here. And I don't know the time frame between all these pictures, but these pictures were taken. And then a while later, as I said, I don't know how many months or years passed between these pictures, but we can't see that supernova anymore. The supernova from that distant galaxy has basically moved out of our ability to see. Here's another one. And then we look down here, and I think we can still kind of see it, but it's much, much dimmer. And you see that that's happening in all these cases. These supernova are getting dimmer and dimmer. You can barely see it in this fourth one here. The same thing, the fifth one. There's the supernova, and it's further and further away. And in fact, the expansion is accelerating. In other words, not only are these far galaxies moving away from us, but the further away they are, the faster they move. And surprisingly, the farthest galaxies are moving away from us faster than the speed of light. Now, you may already know, and we're going to actually talk about it a little bit next week. We're going to do an activity next week where nothing can go faster than the speed of light. And you might say, well, how could these galaxies be moving faster than the speed of light? It's that space itself is expanding, and space-time itself is expanding faster than the speed of light. So the universe is expanding and it's accelerating. We'll talk about what's accelerating it, or what we think is accelerating it, in just a few minutes. So what causes it? We don't know yet. So we call it dark energy. It turns out that the rate of expansion increased, as far as we know, a few billion years after the Big Bang, about roughly 5 billion years ago, we would say. So about 5 billion years ago, the universe seems to be expanding even faster and faster and faster, and the galaxies are getting further and further apart. Now, a reasonable question, you think about the balloon. If we blow the balloon up, at a certain point, the balloon will either break or the rubber in the balloon won't let us blow it up any further. And in fact, if you've ever had this happen, if you let a balloon sit around for a few days, some of the air starts to escape and it contracts and gets smaller again. So you might think, well, what's the universe going to do? Will it just expand forever, or will it eventually come back together? Now, the only thing that could pull it back together is gravity. So as the universe is expanding, the only thing that could pull one galaxy back in towards the center is gravity. And remember, gravity increases with mass. If we remember Newton's law of universal gravitation, a bigger body like the Earth attracts more than people do to each other. It turns out that according to our measurements, we're below what's called the critical density for gravity to contract the universe. In other words, there's not enough matter, there's not enough density for gravity to pull everything back. Now, years ago, we weren't sure about this, and it was sometimes called the Big Crunch. It was an idea that the universe would expand forever and then crunch back down. As far as we know now, that's not going to happen. The universe will just keep expanding and expanding and expanding. Eventually, it's going to expand so much that we won't be able to see many, many stars. It'll be very dim in our night sky. But that's many, many, many years in the future. So the Big Bang occurs 13.8 billion years ago. Sometimes you'll hear the number 13.7. I think it was just recently adjusted, about 13.8. But 13.8, 13.7, that's fine for right now. And where did this come from? Where did this idea come from? Well, Hubble had the idea that the universe is expanding. Well, if it's been expanding, then at some time in the past, it must have been really, really small. The balloon is expanding. Well, it starts out as a regular, real small balloon. And there was a priest, I believe he was Belgian, Father George Lemaitre, and he had this idea that, and called it the primeval atom, that at some time in the far distant past, it was very small. And then a physicist by the name of George Gamow in his PhD thesis, he actually started to do the math and worked out the numbers for it. So Lemaitre had the idea, and Gamow then did the math. And one thing that's important to know is the universe is cooling as it expands. Back when it was this primeval atom, if we want to call it that, back when it was sometimes called the singularity, back when it was really, really small, it was very, very hot. So if we look at this graph here on the right, originally, way back when, the universe was super hot, 10 to the 31 Kelvin or 32, unbelievably hot. And in fact, that's the hottest temperature ever. Now, if you look here at the bottom in terms of time, notice that these are fractions, 10 to the minus 43 of a second, 10 to the minus 33. The universe cools very, very quickly and expands very, very quickly. So the temperature of the universe is going down, going down, going down as time goes on. And in fact, for the first fraction of the second, forces like gravity and electricity, the electromagnetic force and the nuclear forces, were actually, we think, all the same. We really don't understand the rules for these very, very early times because we don't have the physics. The physics didn't behave under the same mathematical laws that we now use. And we're going to go through some of the time frame, but I'll just quickly touch on it here. For the first roughly second of its existence, or less than a second, it was really all light. And then we started to get protons and antiprotons, which are matter and antimatter. Then we can start to get electrons and positrons, and then a little bit later atoms, galaxies, and then the stars. And this looks kind of linear, but it's not. These are exponential. So these are factors of 10 on the bottom as time increases. And we're going to see a calendar to give us an idea of when all this happened. Well, we need evidence for the Big Bang. The first big piece of evidence is the Hubble, is the redshifting of the galaxies. That's very important as good evidence for the Big Bang. Other very important evidence came from two fellows, Penzias and Wilson, who were not astronomers. They were working at AT&T Labs, so they were communications engineers in New Jersey. And they were getting all this noise. And no matter where they pointed their telescopes and their receivers in the sky, they got this noise. And originally, in fact, they thought that maybe something was in the receiver, and they climbed up there and they looked. They thought, is it birds? Is it bird feces? They thought that there was animals were in their telescope and in their receiver, and that's not what it was in their radio receiver. What it was something called the cosmic microwave background radiation, the CMB. Now, we identify this radio waves by temperature. And the temperature is 2.73 Kelvin. Basically, what it was saying was this is the temperature all through space many, many, many years ago. And these were radio waves coming from all directions. What they were hearing with these radio waves was noise left over from the Big Bang. So not only do we have the expansion, they could actually hear the radio waves. So what's going on in this early universe? We know there's a Big Bang. We have good evidence for it. So let's look at just the first 1 second. In the first 1 second of our universe, the whole universe is composed of light. Everything that eventually became you and me and the atoms and the planets and everything we know was light, was photons. Now, a reasonable person might say, yeah, but we have atoms. We have hydrogen and carbon and all that. If you had a chemistry class, you know that. How could light become matter? And it's thanks to Einstein. E equals mc squared. Energy and matter can be converted. Now, the c squared is the speed of light. And actually, I should say there's a longer form of the E equals mc squared, but we're not worrying about that for right now. So this light could actually form what we know are what are called matter and antimatter. So looking over here at this first picture, two gamma rays. Now gamma rays are just light that we can't see. They're very energetic photons, very energetic forms of light. If two gamma rays come together, and there were plenty of these gamma rays, that's what the whole universe was made of initially, all these photons, they can form what's called an electron and a positron, which are matter, which have mass, because E equals mc squared. Now, an electron you've probably heard of, or which assume you know. It's a very light particle with a negative charge. It turns out that a positron, and you may have heard this, especially if you like science fiction or Star Trek or things like that, but a positron is just a positive electron. The electron is matter, and the positron is what we call antimatter. And we think antimatter is weird, but it's really not. Now, there's a little problem. When matter and antimatter come together, when an electron and a positron come together, they destroy each other. And in fact, that happens. They destroy each other and they go back to being photons. They go back to being gamma rays. If the early universe had been 50% matter, 50% antimatter, we wouldn't be here. We wouldn't have atoms as we know it today. And we don't understand the reason for this. But for whatever reason, matter won. There was a slight bit of a fraction more matter than there was antimatter. I don't have the number right off the top of my head, but it was, just like parts in a million or parts in a billion. So there was a tiny bit more matter that survived. And those tiny bits of matter, those electrons, 3 minutes into the universe, these electrons, and we start to also now get our protons and our neutrons coming together and starting to form atoms, things like deuterium. Now, deuterium is just a form of hydrogen. Also forming helium, and it could be 3 helium, which means 2 protons and 1 neutron, or 4 helium, 2 protons and 2 neutrons. So within 1 second, we only have light. Within 3 minutes, we're starting to get subatomic particles like electrons, like protons, and like neutrons. And we should all be very grateful that the matter was able to beat the antimatter. And it's not that it was stronger; it's that we had a slight bit more of matter to win. The universe is also very dense. There's all this light. There's all these atoms in still a fairly small place. After about 380,000 years, and here it says about 300 to 700,000 years, these are estimates, now we're starting to get stable atoms. Not just nuclei, which is just the core of atoms, but actually atoms with electrons going around them. Those are hydrogen atoms. The universe is expanding now, and it becomes transparent. We can't see any further back because it was just too dense, too much matter, too much light, all packed into the same small area. So how have we detected it? The first satellite to do this was called the COBE. Then there was the WMAP satellite. And the current one, kind of the current state-of-the-art one, is the Planck. You say, well, why do we have to know these three? Well, just take a look. Can you see how fuzzy the picture is on the COBE satellite? And WMAP got a lot better. The reds and the oranges are kind of the hot areas of the galaxy, or the universe, I should say. And then Planck was able to get even a better picture. So what's important, especially if we look at the Planck picture here? So the bottom picture, this thing that kind of looks like an egg, really a way to think about it, it's the baby picture of the universe. I'm sure many of us have baby pictures of ourselves and our family. Here's the universe's baby picture. And if we look, the red are the places of hot temperature where there's a lot of matter and energy. The blue, less so, less dense, less energy there. And this is important. It wasn't even. There's clustering. So we can see like all these red clusters. Those are the places where the energy is close together. Because you have that, when things are closer together, now gravity can start to work and the atoms can start to, they're close enough to attract each other. It's because you had this clustering, we had this clustering, that the galaxies and the stars in the galaxies were eventually able to form. Now let's talk about, well, what's the universe actually made of? Here's the really surprising thing. Only 5% is matter. Only 5% is the normal matter that we're used to seeing. You say, well, okay, the universe is pretty empty. Maybe that makes sense. But it's more complicated than that. Only 5% is matter that we know. There's another type of matter that we don't know much about called dark matter. That makes up 27% of the universe. Now, we know dark matter is there because of gravity. Dark matter only interacts with the fundamental force, gravity. It doesn't interact with any other forces. No electromagnetic forces, as far as we know, not the strong or the weak nuclear force. You say, well, how do you know this is here? One way we know is from the rotation of the galaxies. If dark matter wasn't there, the galaxies wouldn't rotate and behave the way we do. In fact, we've now discovered a few galaxies where there's very little or no dark matter. These are some very recent discoveries, and we're not quite sure what to make of that yet, at least as of the time that I'm recording this video. A way I think about matter and dark matter is if you can imagine going into a room, a very dark room, with a Christmas tree that's lit up. The lights would be matter. The lights on the Christmas tree would be matter, for example, the stars and the planets. The whole tree itself, holding it all together, is the dark matter. And what we found even more recently, and it's kind of exciting because these are fairly new discoveries, well within my lifetime. And now I am a little older than most of you folks, but even still, within the last few decades, is this thing called dark energy. And it's 68% of the universe. It's most of the universe is dark energy, and we don't know what it is. All we know is it's there, and it seems to be causing the universe to accelerate its expansion. So let's look at what's going on and how we now a more modern view of the Big Bang. There's this time called the inflationary period. And the inflationary period is roughly the first 400,000 years. When the universe undergoes that first spark, that first Big Bang, and then very fast inflation. Remember, it's not expanding into anything. It's space itself expanding. And I like on this diagram, you see how they put the cosmic microwave background picture there? So for the first roughly 400,000 years, we can't see anything. Things are very, very close together. The particles are very close. Now that's important because they're close together, they get to about the same temperature. Sort of like water boiling in a pot. It's pretty dense in the pot and they all come to the same temperature. And then we start to actually see things after about 400,000 years. The first stars come about 400 million years later. And you can see that number there, 13.77, 13.7, 13.8 billion years. A neat way to think about it is that the Big Bang is still occurring. Yes, there was that period of inflation, but the expansion that began with the Big Bang is still happening. In a way, the Big Bang never ended. And roughly about 5 billion years ago, a lot of good information on this picture here. Roughly about 5 billion years ago, dark energy starts to come into the picture. We don't know where it was before that. If it was there before that, no one knows really what happened. But 5 billion years ago, dark energy is starting to expand, accelerate the expansion of the universe. So a neat thing to look at, and a lot of books do this, they will take a look and say, let's look at a calendar. Let's start the Big Bang with January 1st, which on Western calendars is the start of the new year. It So through January, February, March, we're starting to get stars right around March, and we're not getting the Milky Way until all the way into May. Almost halfway through the year, we're not getting to the Milky Way. Then we start to get more galaxies. Our solar system doesn't really start to form until August or September. And life on Earth begins roughly in September. In October, so think about how far we are into the year, all the way into October. It takes October until we get oxygen in the Earth's atmosphere. Life doesn't appear in any kind of complex form, anything beyond cells, until about November. Then, December 19th, we're almost at the end of the year. December 19th, we get vertebrates. Then we start to get, who are still in the ocean yet. We don't get plants on the land until December 20th. Christmas, we get dinosaurs on December 25th. The mammals, they come December 26th. Think how close we are to the end of the year. Dinosaurs become extinct December the 30th. Humans don't appear until later in the day, December 31st. All the way at the end of the year is when humans appear. So in terms of the whole scheme of the cosmic universe, we have not been around very, very long. Now, before we move on, you might say, well, what is this dark matter? What is this dark energy? It's such a big part of our universe. It's 95% of the universe. Do we know anything? In terms of dark matter, one thing we do know is that it interacts only with gravity. That's the only force that affects it. And as we said before, it's what holds the galaxies together. And we know this because we can watch the galaxies rotate and do some measurements. An interesting thing is dark matter might be important too because it may have helped the galaxies to form. If you think about a toll booth on a highway, so all the cars are all spread out when they're on the highway. But then when they want to get off and go somewhere, especially if they're going to a large city like maybe New York City or Philadelphia or something, you end up with a line. All the cars are bunched together because everybody's stopped at the toll booth because they have to pay their toll or they have to use the Easy Pass and slow down. But no matter what, they have to stop and slow down. So the dark matter might have been that way. As all the regular matter was swimming around, it hit these clumps of dark matter and it kind of slowed them down enough that gravity could take effect. So dark matter really may have been part of the reason why the galaxies and the stars formed. And we do have a candidate for dark matter, and they're called WIMPs. They're this theoretical idea of weakly interacting, very massive particles. The problem is we haven't observed them yet. If we observe them, we might be able to call them dark matter, but the jury's still out on that. Now, what's dark energy? Well, it turns out that according to quantum mechanics, particles can actually form, like let's say an electron and a positron form, but only for very short amounts of time. And by short, we essentially mean instantaneous. This is called the vacuum energy. It says that there's enough this vacuum energy in space where these electrons and positrons can immediately appear, immediately annihilate themselves. Well, the question is, if they appear, can they cause a pressure? And we do know there's vacuum energy. We have measured this. It's something called the Casimir effect. I'm not going to spend a lot of time on it right now. But there's a thought that is that dark energy? We don't know right now. We don't think right now that the vacuum energy would be sufficient to really be dark energy. We think it's something else that we don't understand yet. And the last question that we're just going to take a few minutes to look at is, well, are we alone in this universe? You know, I think it's a fundamental, interesting question. Life's been on Earth. Earth itself is about 5 billion years old. But life hasn't been here that long. In order to have life, you need hydrocarbons and water. You say, well, what's a hydrocarbon? It has carbon and hydrogen in it. Methane's one. Methane is natural gas. It's what we burn on a gas stove or if you have a gas fireplace or a gas furnace. So in order to have life, you need hydrocarbons, you need water, and conditions have to be right. It's what's called the Goldilocks zone. If you know the story of Goldilocks, she needs the bed that's just right, or she wants to eat the porridge that's not too hot and not too cold, more commonly the habitable zone. So the rule for life is follow the water. If there's water, there's at least the possibility of life. And this whole field is called astrobiology. Now, in astrobiology, that's the study of life in the universe. Life is built on amino acids and proteins. That's more a biology course, but amino acids, they're kind of like the train cars that make up proteins, and protein would be the whole train. In between the stars are these huge clouds of gas and dust. This is where the stars form. And it turns out that in these dust clouds, organic molecules are very abundant. You say, well, how does a molecule go into life? The persons who tested this were Miller and Urey. It's a very famous experiment. So what they did was they had basically just a little chemical flask. And in that chemical flask, they put hydrocarbons and some nitrogen and just some very basic organic compounds. The kind of things that you could find out here in the interstellar clouds. So maybe methane and ammonia and things like that. Very simple little molecules. And basically they zapped it with a little bit of lightning, almost like with a taser nowadays. And they started to find that amino acids were produced. So there's this thought that there may have been these hydrocarbons in, wet pools here on Earth, and maybe lightning kind of jump-started, almost like Frankenstein, jump-started the formation of these important molecules. Now, nowadays, we know that their experiment, there's a few flaws. It wasn't perfect, but it certainly still got the basic idea that we could start to form these more complex molecules if we have an energy source. A good place to look for life might be Mars. It's one of our nearest neighbors. Venus is just too hot. We know that. There's a lot of evidence for liquid water in the past on Mars. We can see markings in the soil and on the rocks that suggest that water once flowed on Mars. And they even found that when they did, they did some drilling, and they could find evidence that there, from some of the underground soil, that there may have been water there. The problem is today conditions aren't good for surface life. Water today would boil off immediately. There's so little pressure in the atmosphere of Mars that liquid water just can't exist. It just would immediately boil off. And there's also no magnetic field. So Mars has no magnetic field to protect itself from the solar wind. Any life that tried to take hold, well, the protons and electrons coming from the sun would basically burn it away. Well, the question is it still possible? Maybe. There may be underground water or ice on Mars. And the Curiosity mission did detect some organic molecules there. And you see, this is 2018. This is 2 years ago. And methane was detected in 2019. And methane is definitely an organic molecule. And there was a big stir many years ago about this Martian meteorite. This is a meteorite that came from Mars, and we found it on the Earth. They found it in Antarctica. And they found these structures in there that look a lot like, now we look at it, it looks like a little worm or a caterpillar, but that's very, very small. It could be a cell. Some people posited that it could be a cell. Nowadays, they're not sure because it's very small. It would be, if it was a cell, it would be much smaller than the kind of small animals that we know about. But we can't really rule out that there could be maybe bacterial life on Mars. However, it wouldn't be like intelligent Martians or the alien we saw in the slide a few minutes ago. A couple other places we might look for life. Europa is a moon of Jupiter, and Enceladus is a moon of Saturn. And we think there's oceans underneath their surfaces. In fact, you can see on the picture here, this is Europa, you can see the cracks from the movement of the water underneath. And we don't know. Is there enough internal heat? Are there some organic molecules in there? Could bacterial life exist there? We don't know at this point, But these two moons, Europa and Jupiter, would probably be a place to look because they're the places where there's a possibility of liquid water other than the Earth. And lastly, we'll just talk a little bit about exoplanets, which are planets outside of our solar system. A number of these planets have biomarkers. We have a rough idea of what's in their atmosphere. However, to get there, like to try and go visit and look, it takes too much energy and it would just take too long a time. So the best we can do is look for radio signals. And the longest running project on this is the SETI project, the Search for Extraterrestrial Life. However, they're saying it's kind of like a cosmic haystack. If you've heard the idea of searching for the needle in a haystack, the universe is so big that even if we point our telescopes, we're only looking at a tiny slice of the sky, so it might be really hard to detect a radio signal coming from one of these other planets. You might say, well, what if they're not contacting us? If they have radio communication, the same way we have radios or we have TV broadcasts, we'd be able to pick those up. We haven't yet. There have been a few. There was one called the WOW signal. So there have been some, I don't want to say false starts, but things which suggested maybe. And one of the first people to look for this was Frank Drake in 1960, an astronomer. And he called it Project Ozma. Ozma was supposedly the princess queen of Oz, so he was sort of using the radio signals to try to basically contact the fairyland or contact Oz. That's what he called it. And he has a famous equation called the Drake equation, where he estimates there might be about 100 civilizations in our galaxy which are technologically advanced. That's not very much for the whole size of our galaxy, which might explain why we haven't found them yet. Now, it should be said the Drake equation is it's an estimate. It's a model. I don't want to say it's guesswork because there are some numbers there, but it's just a way to think about, well, how crowded would our galaxy be? Now, we've discovered many more exoplanets since Drake put his equation out, so it is possible that that number could be a little bit higher since then. And then one last thing to talk about is, have we been visited? The problem is UFO evidence is what we would call anecdotal. So just because your cousin saw a UFO or tells you he saw a UFO, and even though many, many people claim to have seen UFOs, it doesn't mean they're necessarily of alien origin. They could be something else. It's not science. Science has to be reproducible. We'd have to have a way to actually find these UFOs regularly. However, and you can see this is April 2020, so very recently, the Pentagon actually released videos from, I believe they were Navy pilots, where they seemed to find or see these UFOs. Does it mean they're from another planet? No one knows. Could be something else. But the pilots obviously saw something that they couldn't explain. And an interesting thing about this is these videos, kind of the Pentagon had to release, and they were already released sort of as a whistleblower or a leak by a member of the pop group Blink-182. He released them, I don't know, on his Twitter feed or one of his social media and released them first. So you can look at them online and you can view them yourself and, make up your own mind. But we wouldn't call them, right now we can't say they're science. We don't really know what they were seeing.